Hello once again and welcome back. So today we're going to very quickly take a look at the topic of electrostatics in A-level physics. Now, electrostatics is simply the study of charges at rest. The study of charges at rest is known as electrostatics. Now, when you're talking about electrical charges, one of the most discussed natures of them in physics is actually the interactions they have with each other, whether they actually, attract each other, repel each other, or the fact that they can create electric fields around them. Today, we're going to go ahead and take a look at a very brief aspect of electrostatics. We have learned, or you may have learned, a couple of things about electrical charges. The fact that there is 3 subatomic particles known as protons, electrons, and neutrons. So the fact that atoms are separated into subatomic particles, and these subatomic particles are none other than the proton, the neutron, and the electron. The proton being positively charged, the neutron having a neutral charge or a charge of 0, while the electron has a negative charge. Now, very specifically, through a experiment known as the Millikan oil drop experiment, we found that the charge of one electron is roughly around negative 1.6 times 10 to the power of negative 19 coulombs. The charge of a proton is the same as the charge of an electron, but it's just positive. So the charge of a proton is the absolute value version of the charge of the electron. The mass of protons and electrons are also there, with the proton being sort of heavier than the electron themselves, with the mass of the electron being somewhere around 9.1 times 10 to the power of negative 31 kilograms, while the mass of a proton is equal to somewhere around 1.67 times 10 to the power of negative 27 kilograms. Now, these values are rather important for questions that involve kinematics. Sometimes you'll be asked to find the speed of an electron or the acceleration of an electron. And so knowing their masses can help because, those questions really connect to Newton's laws. And for finding acceleration, you do need the mass. And you usually just substitute force for the F equals ma as the force of the electric field. Now, there's a couple of laws that you have to be introduced to in electrostatics. The first one is Coulomb's law. Coulomb's law is basically equal to F equals to K, Q1 times Q2 divided by R squared, where K is simply known as the constant of Coulomb's law. So that's the first thing you'll probably cover in electrostatics. Of course, you'll cover some stuff about conductors and charging stuff by induction and sort of those topics. But then after that, you'll probably go into Coulomb's law. This is the most basic format of Coulomb's law, where K is known as the constant of Coulomb's law, and it has a value of roughly 9 times 10 to the power of 9 Newton meter square per Coulomb square. After Coulomb's law, you'll learn about the fact that, positive and negative charges create an electrical field around themselves. Whatever enters that electrical field will experience a force. You can find the force acting on them by using the formula F equals to E times Q, where E is the electric field measured in newtons per coulomb, Q is the charge measured in coulombs, and F is the force measured in newtons. After that, you'll learn that around single point charges, there's also an electrical field, and you can calculate the electric field strength around them by using the formula E equals to KQ over R squared, where K is obviously the constant of Coulomb's law constant, Q is the charge, and R is the the distance to the point charge. Usually, you'll have tons of questions involving, finding the electric field, finding where the electric field is 0, or perhaps questions that involve even tension and things of those natures. What we usually find is a lot of the students have problems with questions regarding vectors and things that involve tension in this course. So I'm going to be going ahead and doing a very quick review and kind of a quick question on tension. And later on, you'll probably see another video on the basics of electrostatics. So let's go ahead and take a look at this question I've prepared for you guys. It says 2 identical tennis balls. By the way, this is a question from the A-level Pearson exam. Feel free to subscribe. You can always use the content created on this channel for yourself if you're preparing for the iMath exam, A-levels, or the IB exam. Now, it says the conducting threads are suspended from the point P, and each of the balls have a positive charge. So both the balls have the same charge, and the mass of each ball is 2.7 grams. Okay. Now, what exactly is the question asking us to do here? Well, it's asking us to essentially go ahead and essentially first draw a free body diagram for the ball m. That's the most important thing you have to do, because once you know the free body diagram, you don't even have to worry about anything else. You can just solve the question very easily after that. So in part A, I have a ball there, so I'm just going to assume this is point P here, and that's the ball. Let's call that ball M, and it's suspended at an angle of 35 degrees, and the length of the thread is just 18 centimeters. Now, here's the deal. The forces acting on ball M are as follows. First of all, there's a tension created in the thread. By the way, if you don't remember, tension is a force created in strings, usually in physics, and it's just a force that breaks even the forces that are pushing down the thread. So it stops the thread from breaking apart, and that's just called T. Another thing that's acting on the thread is the mass of the ball itself. So that's a downward force. We can call that just M times G. It's the weight, and we know weight is mg. And there's also an electrostatic repulsion from ball M onto M. So there is a rightward force where the ball M actually pushes away N, and that's just the F or the Fe. We can call that the electrostatic force. So, are we done with this? Well, actually, we have to complete the diagram. The thing is, the tension is being applied at an angle of, 35 degrees. However, it's being applied diagonally. So we have to make it into two different components, one in the X direction and one in the Y direction. So we're going to go ahead and we're going to draw a line there. Following the rules of, geometry, we can conclude that the angle of the tension is the same as the angle here. The 35 degrees are shared in both sides. So this side also has an angle of 35 degrees. Now we're going to have one tension force in the Y direction. We can call that T of X. We can call that T of Y. And we're going to have one tension in the X direction. We can call that T of X. Now we're going to draw that tension force to the left because that's the only way the ball is going to be balanced. And so that's the only way the tension force is going to balance out the force of the electrostatics, the Fe. So our final diagram is going to look something like this. We're going to have one point charge in the middle. We can call that point M. There is a rightward force due to the electrostatic repulsion, and there's a downward force due to the mass of the ball. We can call that mg. There is a leftward force due to the tension component. That's T of X, and there is another tension force in the Y direction called Ty. Now, how can we calculate Ty and Tx exactly? Well, it turns out that it's as if we have an inverted triangle right above there, and we can find out the trigonometric values we can use for the tension forces in the X and Y direction. So here is the following details. We know that the angle at which the tension is being applied is 35 degrees. We followed the alternate interior angle rule over there to establish that angle. This is T itself. Now, the tension force in the X direction is going to be this line here. I'm going to draw it using the yellow color. Now, this one is opposite to 35. Any angle that is opposite to the theta, original theta, or the angle will take sinus, because sinus is opposite over hypotenuse. So this angle becomes T sinus of theta. That is your component in the X direction. However, the component in the Y direction, which is going to be the green line, or Ty, is adjacent to 35 degrees. And any side that's adjacent will take cosinus when you're trying to solve for its component. So this side becomes T cosinus of theta. So we can establish that Ty is T sinus of theta, and the opposite way around. Ty is T cosinus of theta, and Tx is T sinus of theta, meaning that if you wanted to find the tension in those two components, you have to use these formulas. That's the answer to question part A, which is drawing the free body diagram. Let's go to part B now. Part B says that show that the tension in one of the threads is about the given number. Okay, let's go ahead and do that. Now, we cannot use the tension in the X direction because we don't know what the electrostatic force is, because we don't know the value of the charges, but we can use the tension in the Y direction. We can say Ty is equal to the mass times gravity, or to the weight. That's pretty obvious because, they balance each other out. So we can go ahead and say that Ty is just tension times sinus of 35 degrees. And this is equal to mass, which is 2.7 grams. Convert 2.7 to kilograms. That means we have to divide it by 1,000, multiply it by the amount of gravity. I'm going to, say that the gravity is roughly around 10. So the tension force, if we do the division of the right side by sinus of 35, is somewhere around 0.032 newtons, which is technically roughly or approximately the same as 3 times 10 to the power of negative 2 newtons. So that's the answer to part AI. Why did I get a different answer? Because I used 10 as gravity. You can use 9.8 and you'll get the exact same answer. Now let's go ahead and take a look at number 2. It says, show that the electrostatic force between the two balls, or between the balls, is about 2 times 10 to the power of negative 2. So in part II, we can use the tension force in the x direction. We can say Tx is equal to the electrostatic force. And that will give us the following result. T sinus of theta. By the way, you have to fix the last part because Ty is T cosinus of theta. I made a mistake there. You have to change that to T cosinus of theta. So in part II, in order to find the tension in the x direction, you have to use T sinus of theta equals to the electrostatic force. So tension is 3 times 10 to the power of negative 2. We know that the sinus of theta is just the sinus of 35 degrees. So the electrostatic force is equal to 3 times 10 to the power of negative 2 times sinus of 35. Let me go ahead and quickly calculate that. That will give you a value of 2 times 10 to the power of negative 2 newtons. So that's it. That's going to be the value of the electrostatic force. And we found it by using the forces acting in the x direction, because the electrostatic force balances out the force in the x direction, or the Tx component. We can say that T sinus of theta is equal to Fe, and then solve for Fe. The last part of the question is asking us to find the charge on each ball. So that's actually part I. To calculate the charge on each ball, we know that the electrostatic force between them is Q1 times Q2 over R squared. We can actually rearrange this for charge, and since both of them have the same charge, we can say Q1 and Q2 is just Q. So we can say F is equal to Q squared over R squared. Let's rearrange this for Q. Q squared is equal to FR squared divided by K. So Q is just the square root of FR squared over K. Now, the distance between the balls is 20.6 centimeters. So we can say that Q is simply going to be the square root of the force, the electrostatic force. That's 2 times 10 to the power of negative 2. We found this in the last part. Multiplied by the distance between them. That's 20.6 centimeters converted to meters. So times 10 to the power of negative 2 raised to the power of 2. Divided by the constant of Coulomb's law, which is 9 times 10 to the power of 9. The square root is over the whole part, by the way. So Q is going to be the result of that. You can actually calculate that part by putting it in the calculator. Let me do that quickly. 2 times 10 to the power of negative 2 multiplied by 20.6 times 10 to the power of negative 2 raised to the power of 2 divided by 9 times 10 to the power of 9. The charge is somewhere around 3.07 times 10 to the power of negative 7 coulombs. That's going to be the rough value of the charge. So as you can see, this is how you can do a question that involves vectors at the A-level sort of question level, and also IB. Usually, as I stated, or actually in most of the times, because of the rules of trigonometry, if you have a triangle like this, keep in mind that, let me draw the triangle down. Keep in mind that the triangle like this, if it has an angle of theta, the side opposite to theta will always use sinus. You can find the component using sinus, and the side adjacent to theta can be found using cosinus. So that's going to be the deal. Sometimes the triangle kind of inverts like the one we did before, and as a result, you have to make sure you're using the right trigonometric ratios. And this actually comes from the rule of SOHCAHTOA, where sinus of theta is equal to opposite over hypotenuse, and cosinus of theta is equal to the adjacent side over the hypotenuse. So in the last question, the tension force was here. The tension, so if I wanted to draw the triangle of tension in the last question, this was theta. This was the original tension in the string, diagonally being applied. And the tension in the x direction was this side. This was t of x. And this side was essentially t of y. So if you wanted to find t of x, we had to take the sinus of theta. Now, sinus of theta is the opposite side, which is tx, over the hypotenuse, which is t. So if we solve this for tx will give us t times sinus of theta. So this is the proof of how we got the components in the last, or in part A. Stay tuned, practice hard, and good luck for now.